Okay, so I think we can start. In the last lecture, we started talking about our second family of generative model, which is the latent variable model. That is what we started discussing in our last lecture, although we did not complete it and probably will not be completing it today either. So, what was the philosophy of latent variable model? The philosophy is that there is a cause, there is some low dimensional variable, some low dimensional reason uh, that you can trace back to, and whatever image, whatever high dimensional data you have is a reason or can be represented using those low dimensional factors or features, right? And those low dimensional features or factors are unobserved, so that's why you call it latent or hidden, and hence the name latent variable model, right? And if you remember the examples we talked about, I mean, I gave 3 examples. One was GPLVM, Gaussian process latent variable model, and I said that we will not be discussing this probably. The second thing was the obvious one, which was mixture distribution or mixture of Gaussian to be more specific, is what we discussed. We discussed about it very briefly, but that's not a deep model. And then we started discussing about what is a deep model, which is a variational autoencoder. But we did not complete, I mean, we did not even do 50% of variational autoencoder. And so the plan for today is to continue our discussion on variational autoencoder, right? Okay. So with that background, let us start. So we were talking about latent variable model or models, whatever you call it. And I told you that no matter which latent variable model you use, the fundamental principle will be defined by 2 equations. The first equation was that you sample the latent variable from some distribution. Z is your latent variable, and then you sample your data conditioned on Z from a distribution something like this. And the whole idea is that X is having a complex distribution, but X given Z will have a much simpler distribution. Because when you condition on the feature, you get similarity, which means the distribution becomes simpler. And the example we talked about was basically, I think, male versus female, if you have images of that. So if you take condition on male, then the images will look much more similar as opposed to when you are looking at everything together, right? That is what we talked about. And in particular for VAE, how does it look? So for VAE, which is variational autoencoder, I mean, this is not compulsion, but this is the vanilla VAE, if you may say so. Generally, this is equal to 0, comma I, and your X given Z is also a Gaussian from, let's say, mu parameterized by theta with input Z, and then your covariance theta Z, right? So this is how you represent things in VAE. You can ask why Z is Gaussian. It need not be. Why X given Z is Gaussian? Again, it need not be. This is the simplest choice possible. This is the vanilla VAE, right? There can be improvements over that. For example, one improvement I mentioned was that, not improvement, but one option I mentioned was that X given Z can be mixture of Gaussian. X given Z can be an autoregressive model that we discussed previously, right? Similarly, Z can also be uniform, but or something else, and that's absolutely fine. There is nothing wrong with that. But this is the most basic one, and we will restrict ourselves to the basic ones, because once you understand the basic principles, you can always extend it to whatever modification you prefer for the problem at hand. The principles will not change. Um, the way we will proceed from here will not change. Training will not change. Some calculation might change, and accordingly some terms might get added or modified or replaced, whatever, right? And that's all that will happen, no matter what choice you are making. Yes, the maths might become much more difficult if you make some crazy choice, right? But in short, this is the VAE, or rather, if I go to the top expression, that is my latent variable model that we uh, started discussing and we discussed last time around, right? Now we started also talking about that how to train this model. So you did see this theta in the subscript, which means that your mu is the output of a neural network. The neural network input is z, and the neural network is parameterized by theta. So that is what mu theta means. Mu theta means it's a function, a nonlinear function, a neural network, and the neural network parameters, the neural network weights and biases are represented by theta. And yeah, both mu and sigma. So that's why you see theta in both the places, right? So fundamentally, the idea is that you will sample z, those z will go through some neural network that will give you your mu and sigma. You take those mu and sigma, put them into Gaussian and sample from that. That is the whole idea of this expression. If you have to sample, that's how you will sample. You will sample from z, take your sample, put it into the neural network. The neural network will give you your mu and sigma. Take those mu and sigma, put it into a Gaussian, sample from Gaussian. This is what you are going to do, and this will allow you to sample x, which is the ultimate goal, to learn the distribution of the data. So this will allow you to learn x. But you can only do this if you know theta. If you do not know theta, none of this will work. You will sample z, but then how will you get mu and sigma without the theta? You will not get theta, you will not get mu and sigma without theta, and without mu and sigma, you will not be able to sample from x given z. So that's why you have to learn theta based on some training data, right? And that is what we started. So how to train this model? It can be a single network with two outputs also, right? I mean, does not matter, depends on how many outputs. So training, how so do we train the model? Now, if we talk about training, we discussed it. How do you train the model? You maximize the likelihood of the data. So to train the model, so the obvious choice is MLE, which is maximum likelihood estimation, right? And if I use maximum likelihood estimation, this is how it will look. I mean, you already know this, nothing new here, no surprises. You will maximize probability of d given theta, where d is your data set. If you have images, all collection of images is what d is. If you have time series, all collection of time series is what your d is. Okay, so d is your data, this is your likelihood. You will want to maximize your likelihood of the data, and that will give you your theta. And we have discussed about this maximum likelihood estimation. You can simplify it further. What is the basic assumption we are going to take? IID. So first thing is d is equal to, we write it as x1, x2, and let's assume n such images, so xn. So assuming the data to be IID, we have theta star is equal to arg max product I is equal to 1 to n probability of x I given theta, right? IID, so the product, and then you can find it out. And also we know that we don't work with this probability in general. These are very small numbers in most cases. We work with the log probability. So this is also equivalent to arg max theta, product will become summation. So summation I equal to 1 to n log probability of x I given theta, right? Very basic. But the problem starts from this point. Probability of xi given theta is intractable. You do not know what is probability of xi given theta. You cannot write it, and that's where the problem starts. Because there is z also, so you cannot work with this. So this term, how to compute? So this term, right? Probability of x given theta. I am dropping this superscript I because I don't want to write I again and again. There is no other reason. If you like, you can write I, does not matter. I'm not writing it because I just don't want to write it again and again. That's the reason. So this is equal to, remember that x and z, your model has both. So you have to find out the joint and then integrate out z. So x given theta is basically integration of probability of x comma z dz, right? It's a integral. This integral is intractable, right? Uh, this integral is intractable. You cannot do it analytically. So what we do is that our only hope is to find out some approximation, right? And our approximation in most cases, or at least in this case, we will start with the obvious approximation, which is the law of large number, which gives us the crude Monte Carlo. And this is where there was some doubt, right? When I wrote that this I can represent as integration probability of x comma z dz, right? So what I am doing is that I am taking some high dimensional uniform PDF, multiplying by it and dividing by it. So 1 by that modulus of z that you are seeing is some uniform random variable, right? And so I'm writing it in this manner because I want to express it as an expectation. Law of large number is only applicable when you want to find expectation. Why am I taking uniform? Why not some other distribution? You can, in fact, you can decompose it and then work with that also. But for a generic deterministic function, this one actually shows that any generic deterministic function, the integral of that can be expressed by using or by doing this trick, which is multiply by a uniform, divide by a uniform. So that is what it shows, and that's why. So, and once I write it like this, my Monte Carlo approximation will be uh, 1 by m summation I equal to 1 by m probability of x comma z I, where z is now drawn from the uniform distribution, right? Is z is drawn from the uniform distribution. I think yes, last lecture I forgot to write that factor outside, but that's obvious that that factor will be there. I mean, there is no surprises there. I mean, that's obvious that that factor will be outside. I just forgot to write it last time. I think it was pointed out by someone. Okay, we know this, and we know that using this we can find out the integral. The problem, however, is that this is a very crude way of doing things, and this has very slow convergence. This is the crude Monte Carlo, and this is very slow convergence. If you want exact number, this will converge as 1 by square root of m, where small m, where small m is your number of samples. If you take this estimator, find out the standard deviation of this, you will find out that you will get 1 by square root of m, where square root of m is your number of samples you are drawing. And when it is 1 by square root of m, it means that this is correct, but you will need lot of m's to get an accurate estimate. To get an accurate estimate of the expectation, you will need a lot of m. M has to be a very high number. And we don't want that. We don't want a high number. So this is, so we look into alternative. So we will not use this. Okay. Yeah. Hmm. Correct. It's a function. Correct. Not right. No, why? In the summation form, you are saying? It's not exactly PMF because you are not integrating it. It's become a PMF when you integrate in a small interval and make that. Then it will be PMF. Because I'm not integrating, I'm just evaluating it. It will not be. The reason is that, yes, yes. So suppose take let's say uniform in 0 to 0.5. What is the value? What is the value of the period? 2. Now you evaluate it at any point, you will get a 2. Now is 2 a PMF? It cannot be. It will violate that. So that's why I took that example. But if you start integrating in small strips, let's say 0 to 0.1, you take 2. Then you will start getting numbers which are probability. It will only become PMF if you at least have a finite strip where you are integrating. So that's why it is not a PMF. It is just evaluating that function. Okay. And 1 by m will actually account for that. Because inside terms, if they are not 1 by m will make sure that it, because ultimately this whole thing is representing that integral. Okay. So yeah. So what I was saying is that crude MCS or Monte Carlo estimates are slow, or rather the correct terminology will be have slow convergence. Maybe I should write that. So which means it have slow convergence, right? The Monte Carlo estimate has or have slow convergence, and so we don't want to go that route because we will need lot of samples. One easy alternative to Monte Carlo is what is known as importance or important sampling. How many of you have heard of important sampling? I see maybe 20%, 30%. So important sampling, I will discuss that very briefly. So, and then we will see how we use it, right? So, one option is to use important sampling, okay, which is also known as IS. The idea of important sampling is that you sample from a distribution which has high probability mass with the original one, which means instead of taking uniform, because in uniform what will happen, you imagine a Gaussian, right? If you take a uniform near, let's say 3 to 5, a standard Gaussian, you know that the probability masses you are going to get, or not probability mass but PDF values, those will be 0. Those will be very small, because the Gaussian is from -3 to +3 with 99.81%. So beyond that, that percentage is very small. So the density values will be very small, right? So if I have to do important sampling for a Gaussian distribution, I should select preferably in the range -3 to +3. And with not only that, I should sample more from, let's say, -1 to +1 than from 1 to 2. So that is the idea of important sampling, that you, because this distribution, right, need not be uniform, it can be any distribution. So you select a distribution which will give you larger values of this P, that is finite or larger probability density values. In a nutshell, that is the whole idea of importance sampling. Okay. So if I use importance sampling, so what will I do? Is very simple. So in IS, remember I want to evaluate this integral, right? Probability of x comma z dz. This is what I want to evaluate. Instead of multiplying by a uniform, I will multiply by some density and divide by the same density. And that will now not be uniform but something else. And what is that, we need to find out. So this is equal to integration of qz probability of x comma z qz, right? This qz has a name. It is known as the important sampling density. This is known as important sampling density, or in short we call it ISD. Okay. Now with this ISD as my PDF now, can you tell me this expression is an expectation? Is that an expectation? And if it is, then expectation of what? Expectation of a function P Q, right? With important sampling density as my PDF, I know my expectation is equal to integration of hx fx dx. Hx is the function, fx is the PDF, and then dx. In this case, my fx is equal to q of z. So my fx, so my hx will be equal to this ratio. This means this is equal to expectation z from q p x comma z by qz, right? Everyone follows? Very simple, right? And now it's an expectation. Now I have my tool, which is the law of large number. So I'll use the law of large number, and that will give me what? That will give me it as a summation. So let us use the law of large number. Using law of large number, what we get is this is approximately now equal to 1 by m summation I equal to 1 to m p x comma z I. Actually, I should use j here. Okay, j divided by q z zi zi. This is I. Okay, right? Clear what happened just now? The expectation. Any expectation, we know whatever is the function, we will evaluate it at different sample values, and that will give me my expression. The good thing is that this is an unbiased estimator. If you take expectation of this estimator, you will recover what you actually wanted to estimate. So if you take expectation of this, you can show that it's an unbiased estimator. Okay. So important sampling gives us an unbiased estimator, not always, but in this case. Okay. There are cases or special types of important sampling which are actually biased. This one is unbiased. Okay. So it's an unbiased estimator. If you take expectation, you can recover, which is a good thing. Okay. So important sampling provides an unbiased estimator or estimation of expectation. Okay, this estimation is unbiased. So if you take expectation of this estimation, you will get what you actually wanted to estimate. Okay, remember that whenever I say that some estimator is unbiased, that means expectation of the estimator should give me the original quantity. That's what it means. Expectation of the estimator should give me what I wanted to estimate. For example, sample mean, if I take estimation of sample mean, I'll get the original population mean. So sample mean is an unbiased estimator of the population mean. So that is how you look it and do it. Okay. So this is an unbiased estimator, and that's why it is very popular. Okay. The problem, however, is that we do not work with that expression in top left. In practice, what will we work with? Do we work with the likelihood or log likelihood? Right? So in practice, we want to estimate the log of integration of the probability. So if I put a log here, that becomes an biased estimator. So log of this estimator is not an unbiased estimator of the log of the original quantity. So however, we want to compute or we work with log of p x given theta, right? The log likelihood, which is equal to log of integration of probability of x comma z given theta dz. Okay. And now if you put the importance sampling density instead of for that integral, you get log of that estimator, and that's an unbiased, that's a biased estimator. That's a biased estimator, and you can check it. If you just take m equal to 1, you will realize it will not work. Okay, I'm not going there because that's not the focus. Importance sampling is actually not the focus, so I'm not going there. But it's a biased estimator. Okay. So what to do? We have this expression, right? Which actually, if I write it in terms of the importance sampling, the first step, I have something like q of z, p of x comma z given theta by q of z dz. Okay, this is what we have, right? And you can write now it as an expectation, that's fine, but you cannot use the sampling. The sampling becomes biased, everything else is actually fine. Now, what kind of function is log? Concave. Log is a concave function, right? It looks like this. Because log is a concave function, and inside that quantity is an expectation, right? Inside the log, whatever is sitting is a expectation. So what we have is log of expectation, or log of summation, or log of integration. What we can use is something known as the Jensen's inequality. Jensen's inequality allows us to put this log inside the summation, and that gives us a lower bound of this expression, right? So I think yesterday in practical I mentioned it slightly that this quantity I can think of it as expectation with respect to z from q x comma z given theta by q of z. Okay, and using Jensen's inequality, this is a very useful inequality, by the way. Okay, this is very useful in many problems of statistics and also machine learning, specifically when you are dealing with distributions and all, log and expectation kind of thing. So using Jensen's inequality, let's see what happens. log of p x given theta is equal to log of integration of qz probability of x comma z given theta by qz dz, which is greater than equal to, so that means is the lower bound, expectation of, I mean, okay, basically it is going inside the expectation, log of probability by q of c. Okay, so what I have done, expectation, it was log of expectation, so log of expectation is greater than equal to expectation of log. That's what Jensen equality is when applied to this problem. Jensen equality is much more broader, it's not only to this, but log of expectation is greater than equal to expectation of the log. Okay, you, and the proof of that will be given in your homework 1. Bhagis, take a note. This is one of the small questions, let's say 1A1, something like that, you will get. Prove the Jensen's inequality. I mean, the proof you will get anyways in the Wikipedia, but you should know, so I will give it. Okay, in the Wikipedia you will get the proof of this. Okay, so yeah, so what happens? Log of expectation is greater than equal to expectation of the log, and that's what you see. This is expectation of the log, right? That function. This quantity has a name. It is known as evidence lower bound. This is the evidence lower bound. Why such a name? Because probability of x is like probability of d, which is the evidence, and is the lower bound of that evidence. Okay, so this is known as the evidence lower bound or elbow. Okay, any question? How? It is evidence. This is lower bound of what? Probability of x given theta, right? What is probability of x? Probability of d. What is probability of d called? So lower bound of the. Okay. So evidence lower bound. This is the evidence lower bound. Now, if you have a lower bound, what's it to do with that lower bound? If you have a lower bound, let's say a function, can you use that lower bound to find some parameter? You should maximize the lower bound. Suppose I have a function, I have a lower bound. You will try this bound to be as tight as possible. So you will try to take it closer to the actual function. Because it's a lower bound, you will try to always maximize. This is a trick that is used quite commonly in probabilistic machine learning. You find out the evidence lower bound and try to maximize that. Maximizing the lower bound means what can be the best thing? It can be equal to your original function. So that's the best case possibility you can have. So evidence lower bound, when you have, you try to maximize it. And if you have an upper bound, which you don't have, but then you try to minimize it. Okay. So that it matches with the function. That's the idea. So this is evidence lower bound, and this is what we will work with. This is what you work with, because this you can actually estimate using sampling quite efficiently. Sampling, not analytically, but it is efficient to evaluate this using sampling, and this holds for any choice of q. No matter what q you choose, this expression holds. This is not true. It is not the case that for a certain value of q or a certain choice of q this will work, and for other choice of q it will not work. No, it is not like that, because this derivation was or is independent of any specific assumption about q, which means this holds for any distribution, right? But there is a catch here. If you take a good distribution or so-called good distribution. What good means, I'll come to that later. But if you take a good distribution, then it will converge faster. If you take a bad, it might be even worse than the original crude one. So selecting Q is very important. It holds for any Q, but in practice, you need to select a good Q to evaluate this efficiently. Okay. So let me write this down, these things. So we will work with elbow, and for elbow, let me give a notation. Maybe I will write LQ. Okay, for now I will write elbow as LQ, small l. Capital L I'm not writing because that I will use probably for loss function later, which will be based on elbow, but to distinguish that I am writing small l. Okay. So we will work with elbow, which is L of Q. This is for this holds for any Q. I mean, this is just a fact you should know. But for faster convergence, we need to select a suitable Q or Q of Z. Okay. And naturally the question comes, what is a suitable Q in this problem and how do we find that? Right? The question is simple. What is a suitable Q in this case? Maybe what is the optimal Q in this case? And how do you find it? So what will be the optimal Q in your case, in your opinion? Where that greater than equal to will become equal to. Optimal Q will be one where that greater than equal to will become equal to. So that the left hand side and right hand side will become same. So it will become an exact instead of an upper bound. The optimal Q is one where this equality will hold. Right? So what is that Q for which the equality will hold? This is what we want to answer. Okay. So finding the best Q. Okay, and we in the because we want to find the best Q, let us start with a KL divergence between these two quantity. I mean, ideally I should operate on that and arrive at that because I know I will start with this. So a one page will reduce to 3 lines. P of x. Okay. Okay. Let us start with this scale divergence. If I the scale divergence, if I expand, what will I get? You know that integration of q log of q by p, right? So this is equal to, and okay, I can also write z given x comma theta also I can write. I'm not writing that. I mean, it will not be that theta, but it will be some additional theta that will come. But yeah, I'm not writing that. I'm doing it assuming I can do everything. There is no neural network. This is equal to, you know, integration of qz log of qz dz. Okay. Now the denominator, use the product law. What will I get? X comma z divided by x, p of x, right? So this is equal to log of q of Again, the condition on theta I have not written. I mean, I'm assuming that I can find it out without the need of any neural network. But if the neural network is there, so be it. It will just be conditioned on theta. Nothing changes. This remains as it is. Just for brevity, I'm not including theta. Okay. Now, I will use, I'll separate it out into two terms. The first term I will write is integration of uz log uz by p x comma z, and the second term is plus, what will be the second term? Log p of x, there is nothing upon has been taken care of previously, right? Okay, everyone follows? So if everyone follows, now let us go and you will tell me two things. This expression, what is this equal to? Think carefully. That is correct, but that is useless. But think carefully. The integration is over what? So, so what will happen to log of px? So what is remaining inside the integral? What is integration of q? So what you are getting? What is log of px? Log likelihood or log evidence. The thing that I wanted to estimate in the first place, right? The upper bound of what, the lower bound of which I was calculating. So this is the same quantity, right? So this is equal to, so that I'm not writing theta again, but keep in mind that the theta is there. Okay. Okay. The first term, what is it? Take a minus outside and then think. Consider a minus outside and then think what is the first term. It is the elbow, minus elbow, right? If you take a negative sign outside, the denominator, the log denominator and numerator will exchange, and that is the elbow, right? That elbow is, I think, written somewhere in the previous slide, but yes. So this term is my minus L cube, right? So what am I getting ultimately? What I'm getting is L divergence of Q of Z, probability of Z given X, plus L of Q, oh small l, sorry, let me delete it. L of Q is equal to probability of X given theta again. I am not writing, right? Log, correct. Thank you. Right. Okay. This is clear? Not difficult, right? So now think about it. KL divergence is, what is the range of KL divergence? Greater than equal to 0, right? KL divergence is always greater than equal to 0. It is a property of KL divergence. It cannot be negative, right? So now when will the right hand side and LQ will become equal? When the KL divergence goes to 0. As long as KL divergence is positive, LQ will always be less than log of P, and that's how it is the lower bound. So the equality of the elbow holds when this KL divergence goes to 0. Everyone agrees? So this implies the equality of elbow holds when KL Q is equal to 0. And when KL divergence becomes 0? Same. So what does it mean? What is the optimal QZ? Probability of Z given X. This means when Q of Z is equal to probability of Z given X, then the elbow will become exactly equal to the log evidence. Clear? So the equality holds when KL goes to 0. And when KL goes to 0, then Q is equal to P of X, Z given or Z given X. Okay. So this implies log of probability of X will be equal to L of Q when Q of Z is equal to probability of Z given X, right? So then if I go back in this expression, right, I want to find out theta, keep that in mind. Theta I was not writing, but theta is what I want to find out. What should I use as Q? Probability of Z given X, that is the optimal Q. So I should be using probability of Z given X as my Q. But what is probability of Z given X? You don't know. Can you find it out? How will you find it out? You'll try to use the product law or some law, something like that. Use the product law. Probability of Z given X equal to what? Probability of X comma Z divided by probability of X. That is what we want to find out. That is intractable in the first place. So we go back to what we wanted to find out and we cannot basically. So we could not find out probability of X. That is why we said we will do elbow. In the elbow, we ended up with probability of Z given X. Now to find out probability of Z given X, I need P of X. So it's a chicken and egg problem, right? You cannot work with that. So what we'll have to do? You have to come up with some approximation of Q of probability of Z given X. So some approximate Q which should be as close as possible to the probability of Z given X. That is what you will have to work with, right? So therefore, let me write it down, whatever we discussed now. Ideally, we should use, ideally we should use QZ is equal to probability of Z given X in elbow, because that means it will no longer be an elbow, it will be exactly equal to what we want to find out. However, probability of Z given X we know is equal to probability of X comma Z divided by probability of X, and this quantity is intractable in the first place. I mean, we don't know this. If I know this, then I don't have a problem in the first place. I'll just sample from it, right? This is what I don't know. So this is unknown or intractable, whatever you call it, right? Which means we cannot work with probability of Z given X exactly. That is what it means, that probability of Z given X, we cannot use it as Q of Z. So therefore, we cannot use the the ideal choice. Now, coincidentally, I know some of you did the reliability course, and if you remember in reliability also in importance sampling, the optimal importance sampling density was a function of probability of failure. This always happens in importance sampling. You will never be able to use the optimal one. Okay, so that always happens. So we cannot use the uh, ideal choice. I mean, we don't have an option, right? So what we do is that, so basically then what is our option? So we take Q of Z from some family of distribution, let's say Gaussian, let's say mixture of Gaussian, let's say uniform. We take it from some family of distribution of distribution. We take Q of Z from some family of distribution and then tune the parameters of those distribution to make it as close as possible to probability of Z given X. Some family of distribution and tune the parameters of Q of Z such that it is as close as possible to probability of. Clear? I'll repeat the whole thing, what we observed. What we observed is that we wanted to find optimal Q. And we ended up with the scenario where optimal Q is probability of Z given X, which we cannot work with. And so what we are saying that, okay, then we have only one option. Let us assume Q from some tractable distribution, which we can sample, and then change the parameter of those distribution. For example, if I assume Q to be Gaussian, I will change the mean and standard deviation or mean and covariance. If I assume Q to be uniform, I will tune the lower bound and upper bound, and so on and so forth. You can assume any distribution, right? So we assume some family of distribution, tractable family of distribution, and then tune the parameters of that distribution so that Q of Z is as close as possible. It will not be exact, as close as possible to probability of Z given X, right? This Q of Z with this setup has a name. It is known as the variational distribution. So the idea of variational distribution or the idea of variational inference in general is that when there is a distribution which is intractable, you assume a tractable distribution and then tune the parameters of the tractable distribution so that it matches as closely as possible with the intractable distribution. This whole idea is known as variational inference. And Q, which is your proposal density or assumed density, is known as the variational distribution. P of x, Z given x in this case will be known as your target distribution, because this is what you want to match. P of Z given x becomes your target, Q of Z given becomes your variational or proposal, and you want this to match. No, you don't. You don't. You have samples from X, but not even from this one. You don't have. Right. It never does. The idea of generative distribution is to learn the distribution of your data. So the question of out of distribution generally is not valid for generative design until unless you're doing something. So your whole objective is to learn the distribution of the data. So then what is out of distribution even mean? So in this problem setup, that does not that is not valid. I mean, people are now trying to do it, that how can you fast tune it very fast to some other distribution. But in general, by definition, that does not exist. When you are trying to learn the distribution, what is out of distribution? Right? Any doubt on this? Is the philosophy clear? Clear? We'll see. That too. I have this remaining lecture and the next lecture for that. We'll see that. I have time for that, but we'll see. Okay. Right? So now, let me give the names here actually. This is, I said, is known as variational distribution. Can someone please close that door? The sound is disturbing. Thank you. Right? And this is, I said, is known as target distribution. Now, normally, let us talk about normally, right? Suppose you, normally what will you do? How will you try to find it out? Normally, how will you try to find out Q of Z in this case with this setup? I said QZ should be as close as possible to probability of Z given X. So you will KL divergence, right? That is the obvious choice. So this is equivalent to minimizing KL divergence between Q of Z and P of Z given X, right? But clearly you cannot do this because P of Z given X you do not know, you have no samples, how will you do this, right? So what you do is, I have already given you the clue how to do it. The clue is here, first equation. Minimizing KL divergence means maximizing elbow. Elbow I know. Elbow I can evaluate. Elbow is a function of Q. And by default, because it is function of Q, it should be function of the parameters of Q as well. So instead of minimizing KL divergence, what should I do? Maximize the L. So instead of minimizing KL divergence, we maximize L. And L is now function of Q. It was always function of Q. I mean, that's how I wrote it, right? And initially also I wrote L as a function of Q. So we'll try to maximize the L of Q. And that should give me my Q. But that is also supposed to give me my theta. You're telling something? No, there is no. X comma Z is there. X given Z is not there. Or Z given X is not there. Z given X, you don't know anything. X comma Z you can sample if you know Z. Okay. Because this Q you are trying to learn, right? So Q you will assume it to be, let's say, Gaussian. The moment you assume Q to be Gaussian, you know how to sample from Gaussian. And using those samples, you will try to optimize what should be the mean and standard deviation of the Gaussian. Okay. So have some patience. We're going there. Okay. You are anyways jumping the gun too much, but yeah. Any question? So what I'm saying is that instead of minimizing the KL divergence, we maximize L of Q, right? But actually we are restricting Q to some family of distribution, right? So practically we do not optimize for Q, we optimize for the parameters of Q, right? So in practice we optimize for parameter of Q. Okay. For example, if we assume Q to be Gaussian, then we will optimize or we'll try to find out the parameters of Gaussian, which is mean and standard deviation. Okay. And that helps me convert this variational problem into a variable based problem. This is variational because Q is a function. So I was optimizing over function. That means I will need variational calculus. But by converting into some parameters of Q, it's now variable. So instead of now finding out the optimal function, I will find out the optimal parameter. That makes our life simpler. Your usual calculus will be used instead of variational calculus. Right? That's how it becomes a little bit simpler. Okay. So in practice, we optimize over parameters of Q, and let's call those parameters phi. Okay. Let's call those parameters phi. Now there is one more difficulty that is there. What was the KL divergence we are trying to maximize or minimize? Minimize. This one. What is the right hand side of the KL divergence? Probability of z given x. You have training data, right? For training data 1, you will have probability of z given x1. For training data 2, you will have probability of z given x2. These two distributions, will they be same or different? They will have to be different because x, the conditioning variable is changing, right? So that means you have probability of z given x, n numbers of those, one for each data point. You have to find out q how many? N. For each data point, there will be a separate variational distribution, which will make our life even more difficult. This is definitely not tractable what we are doing, but this will become the motivation to go towards something that is tractable. Okay, probably will not go today, but this is setting up the motivation towards going towards what is actually VAE. That is, as I'm sure many of you have seen that, what is VAE, and you can clearly see that we are not even close to that. There is no encoder yet, right? So these are all stepping stones using which you will reach that encoder part. We are now only discussing about decoder since last lecture, right? We will go through the encoder path, and these are whatever we are discussing are the stepping stones, are the mathematical motivations that will take us to that encoder part of the autoencoder. Okay. So another observation is that additionally, probability of z given x is a function of training data, observation, training data, whatever you like to call it, right? Therefore, because it is function of training data, you will have, so we will have probability of z given x1, which is my first training data, probability of z given x2, which is my second training data, and you can go up to nth training data, which is probability of z given xn, right? Is this clear? Because this is happening, I will naturally have, because of this. So accordingly, we will have q of z semicolon phi1 q of z semicolon phi2 and up to q of z semicolon phi n. So you will have one variational distribution per data point, and the parameter phi will not be scalar, it can be vector. For example, if I take Gaussian, I have two parameters per data point. Total number of parameters is 2n, right? Because I have to assume it to be Gaussian. Again, univariate Gaussian. If I assume it to be multivariate Gaussian, then obviously the parameters will be more, quite naturally, right? But are you with me till now? So if you're with me, if this was our setup, if this is all we need to do, how will my algorithm look like? Let us try to write down the algorithm, training algorithm, with this setup. Okay, that how will our algorithm look like? And again, I repeat that this is not going to be tractable. I am sure all of you can follow that there is too many things that are coming into the picture. We'll need to reduce those. We will reduce those. Not today, but we will. But quite clearly, this is not tractable, and that is quite easy to follow, I will say. So the algorithm will look something like this. And this algorithm is kind of a summary of whatever we have discussed till last lecture, right? I mean, after doing all of those things, we have arrived here. So this is kind of a summary of whatever we have discussed till last lecture. Step one. Step one is you will initialize all your parameters. What are the parameters you have? Phi1 to Phi and theta. Theta is common. The decoder part is common. There is not theta 1 to theta n, but phi you have. So initialize phi1, phi2, phi n, comma theta. Right? Step 2 is, remember that whatever you are doing have to be done data point wise or data set, each data point or each image wise, right? So therefore step 2 should be select a data point, let's call it xi, at random from the data set is D. So from the data n data you have, you select one data point as random, and that one data point is an image or a time series. So even though I'm seeing one data point, it's not one point. It's a high dimensional data, obviously, because one point will not use generative model. We'll just do some curve fitting or distribution fitting. So it's high dimensional. If like x1 or xi can be an image, can be a time series or something like that, right? Can be a graph, right? Now once you have this, step 3 is optimize for phi I, right? You will optimize for phi I to obtain let's say the optimum value is phi I star. And here if I have to write, I will write let's say A phi I is equal to phi I plus eta gradient with respect to phi I of the elbow, right? And elbow is function of, now I'm writing all the parameters that elbow is function of. It is function of x I comma theta comma phi I, right? Elbow is function of your data, of your decoder parameter or whatever the z2x parameter, and obviously also your variational parameters. So right now you have initialized theta and phi. You keep theta fixed at whatever you have initialized. You take one data point, so x given x becomes fixed. So the only change will happen in phi. So you update it. You see there is a plus sign instead of a minus sign because it is gradient ascent, because we are maximizing. If we are minimizing, that positive will become negative. So gradient ascent, that's why you see the positive sign. And this you will repeat few number of times until you are happy. And once you are happy, you will say that, okay, I have obtained my obtain pi star, right? Basically, when it converges, let's say 10, 20, 30, 100, whatever, right? That many number of times, iteration you will run it, and for the same data, the data is not changing, by the way, until you reach some level of convergence, right? Once you reach some level of convergence, now you freeze phi, because you have some good estimate of phi, we'll assume, right? And you go outside this, and you will find gradient with respect to theta L xi theta phi star actually. So you phi I at phi I star, which is the best value you got previously, you fix it there. You got your xi, you already know. Theta now is a variable. So that's why you take the gradient with respect to theta. What will be the next step? You know, ascent. Again, you will do gradient ascent of theta. So phi will be update. I'm not writing because update theta. So this will be equal to theta plus, this was eta, let's call it eta 1. So this will be eta 2, let's say, gradient with respect to theta L xi comma theta comma phi star. Update theta and go to step 2. Step 2 is you will again select another data, and this thing will go on until convergence, right? They will go to another data and this will go on until convergence. Please take a close look at the algorithm and let me know if there is any doubt. If the steps are making sense or not, based on whatever we have discussed in last lecture, if the steps are making sense or not. Theta, I am doing just one step here, but you can do more also. But it will not optimize because for each sample it is a function, so it will go on like that. Yes, and ultimately it will converge hopefully at some point. It's a stochastic gradient descent, right? There is no guarantee it will optimize, but that's how it works. Phi was parameter of Q. So example is, if Q is Gaussian, phi is mean and standard deviation. Right? And theta is parameter of a neural network. Yes, go ahead. Yes. Yes. 2000. Yeah, 1000 phi, but each one might be vector. Because mean and standard deviation, I said that example. So each phi is like mu and sigma. So 1000, you have 1000 mu and 1000 sigma. If it is 1D. If it is 100D, then 100 times 2000, and plus if you take diagonal, 100 times 2000, assuming 2000 data, right? So, or 2000 times 100, whatever you call it. So that's how, yeah. Yes. You will face, and that's why it's that scheduling problem has to be solved, and you have to decide that how many epochs of this you will or how many iteration of this and how many iteration of this. So that will happen. I mean, ultimately this algorithm no one uses because this is not yet VAE. I mean, when you go to VAE, you will see that we'll optimize together. So ultimately, this was the original one, but no one uses it. Obviously, you cannot use it, right? But yeah, when you go to VAE, theta and phi will be trained together, right? So then it, yes, yes, you were saying so. 3A, right? Okay. So L, okay, first of all, what is phi? Let's start from there. Phi is the parameter of your variational distribution. And variational by distribution by definition is an approximate distribution. You want your Q, which is your variational distribution, to be as close as possible to the probability of Z given X, right? So there is an optimization problem sitting there where you want to match your QZ and probability of Z given X. And how will you match those? By changing or finding the optimal value of phi. So that is what we are doing here. But remember, we also said that we will not optimize for K. We will not optimize for KL divergence. Instead, we will maximize L of Q. So that is why you see here L of Q, which is X, theta, and phi now. We are trying to maximize it to find out the variational parameters of the variational distribution. What will this ensure? This one will ensure that your variational distribution is as close as possible to the original one. Okay. Next, I'm going to draw a schematic that will explain it better, but let me try it. And is it making sense or not? Repeat once more. How matching? Correct. This one, right? This is what I want to, ultimately, whatever you want to find out should maximize your log likelihood, which is the right hand side. Now, right hand side is equal to the summation of the left hand side, right? Now, assume you have a theta, which is perfect for P of X. That means you have exactly learned your, in the best case scenario, if you have the optimal theta, P of X given theta is fixed. So if I fix theta, right hand side is fixed. You follow that? Now if right hand side is fixed, I want to minimize the first term. Is it not equivalent to maximizing the second term? 1 plus 4 is equal to 5. 5 I have fixed. Now this 1 I want to make it 0. Then 4 I should make 5. So minimizing that becomes equivalent to maximizing the second term. Right? X plus y equal to z. Z is fixed. X I want to minimize. I'm saying no, X is not tractable. I will maximize y, which will equivalent to minimize this. Okay. Yeah. Any other question? If not, let us try to understand this also graphically what is happening, right? Little bit. Graphically, probably you have something like this, let's say, okay? And this is your, I don't know, this is your, let's say, log of Px given theta, okay? If you fix theta, this line is constant. This distribution or whatever it is, right? It is constant, correct? Now, at when you are optimizing phi, so let's say you are here. So at this point, this is your theta, okay? Theta axis. So suppose at this current time step, I am at this theta. Okay. What is the theta I want? Probably somewhere here. That's okay. So at this point, let's say my variational distribution looks something like this. This is my Q, right? Or you can also think of, yeah. But I'm not drawing distribution, so it's not Q actually, it's L, the lower bound. This is L as a function of whatever data point you have. I'm not writing that, but also function of theta and phi. What you are doing is that by changing this phi, you are trying to make this as close as possible to this. That's the lower bound, right? You're trying to match the lower bound with the p of x. And if I look into KL divergence, this is your KL divergence. So you are saying that I will push this curve upward, which means this KL divergence will automatically go towards 0. This is what you are doing to find out your phi. Once you have your phi, now you are updating this curve. Maybe this theta is getting updated. Maybe next step theta goes here. So maybe the next phi you will get, next L you will get will be probably something like this. I don't know. This is again a new theta, new Q or L you are getting, new L you are getting for your updated theta. So sequentially you are trying to do two things. When you are updating phi, it is like pushing your variational distribution towards your original distribution, which means pushing your elbow towards your original log probability. That is what optimizing for phi means. And once you have pushed it to the maximum, now you cannot do anything by changing phi. Now you are saying, okay, for this, what is the theta I should have? You are updating theta going to a new place. And then locally also you will again fit. This is actually, it has a name. We are not exactly using that, so I'm not using that name. You also should not, but the name is expectation maximization. There is an algorithm known as expectation maximization. This is motivated from that. You cannot do expectation maximization directly here because it is intractable in this case. But this is actually synonymous or motivated from what is known as expectation maximization. Okay. So what we're doing is we're doing two optimization problem. One optimization problem will try to maximize my L, which means it will try to match L with P, a log of P of x, or it will try to match Q of z with P of z given x, and that will give me my phi. And then for that phi, I will update my theta so that it moves to a better position. So this is essentially what is happening here. Will mean it's very simple. See, when you did this, right? You got this one is your optimal theta, right? Because you remember you found out theta based on this. So what is your optimal theta? This one, right? And if you stop here, you know this is not your optimal theta. Your optimal theta is somewhere here. So that's why you kind of move it, keep on moving this p also. Exactly. So that's why it's very expensive, right? You have so many parameters and then you have nested loop, which is the worst kind of thing you can have. And nested loop in deep learning is always avoidable. But that's exactly what you have here. You have an outer optimization loop and an inner optimization loop. I mean, that's the worst case scenario kind of what you're looking at. I mean, you at the very least, if they are decoupled, it's still fine. But they're coupled here. So coupling is the worst case scenario. One loop inside the other, right? If there are two loops, serially that was still better. And that will have at some point, but not here. But so yeah, so that is the idea. Any doubt or any clarity on this that you need? Any more clarity you need? Yeah. Yes, it will try to move this what sky color curve up. That's what maximizing. So what is KL? KL is difference between these two curves. You will try to maximize it, which means you will try to minimize the KL. That's what it means. We'll try to maximize it so that it matches, and to the extent possible. I mean, the best case scenario will be at that point it will touch. It will be a tangent or something like that, right? That's the best case scenario. And then at that point you find theta, and then you update theta, and it goes on. Any question? Mostly we look into only one criteria, or everyone looks into one criteria, how quick it will converge. And at the deep learning, at the end of the day, it is all about how fast the convergence is because it's already very expensive. So at the end of the day, biased, unbiased, if it was converging fast, we would have used the biased one. That's how it is. Okay. At the end of the day, it's how fast it is converged, how few sample you will need. That's all. So I'll stop here for today. There are two things that are remaining actually on this, that will take time. One is computing this gradient. We need to compute this gradient. Gradient of with respect to theta is very simple, but gradient with respect to phi is non-trivial, because remember that you are sampling from z, which is a function of phi, and you want derivative with respect to phi. So that will create some problem. We'll talk about the reparameterization scheme next time. There is also the reinforced algorithm, but I will not talk about that now. And then from there, because this has problem, we hopefully everyone acknowledges that because of this whole large parameter space, because of the nested optimization loop, we'll from here go to the amortized version or the VAE, where theta and phi will be optimized together, and how autoencoder will come into picture. So this is what we will do next lecture. Now, for those who were not there yesterday, there were some announcements I make, so I'll repeat those. Practical submission will open today night. You will have 4 or 5 days for practical submission. I already gave much more time in this time because I wanted everyone to get habituated with the deep learning part if you have not done a deep learning course. But those who have done deep learning course, you have already done, it's okay. It was practice for it. Second thing, Friday lecture will be practical. This Friday lecture time, the practical will take place. Okay, where the discussion will be around basic CNN. If you know CNN, you don't need to attend. If you don't know, probably attending is a good idea. I will not be taking the class, the TA will be taking the class. And that's why it's a practical. And instead of that, Monday, next Monday, from 3:30 kind of thing, we'll have a lecture. Okay. And that lecture will not be in the same room where the practical happens, but will be probably somewhere here. I will have to book the room. I'll book the room and communicate to that. Basically, I'm not here on Friday. So that's why Friday is practical. And instead of that, the Monday will be the lecture. And Monday we'll wrap up our discussion on latent variable model. Next, we'll either go to GAN or flow-based normalizing flow, we'll see. Okay. Remember that conditional, we are not discussing intentionally conditional generative models, because I want to give a flavor of all the unconditional or the basic ones, and then we'll go to conditional one by one at the end. Okay. That is all. Thank you.